Hi class, this is Sir Alex Basco and welcome to our lesson in General Chemistry 1. Today we are going to discuss lesson 5 and tackle all about chemical reactions and chemical equations as well as balancing equation. At the end of today's lesson, what I want everyone be able to do is for you guys to be able to write and balance chemical equation. So let's begin our discussion by understanding what chemical reactions are. Chemical reactions is basically a process in which one or more substances, which we usually call reactants, are converted into one or more different substance called the products. So in chemical reactions, you always have your reactants, which are your beginning substances, and then you end up with what we call a product, which are your ending substances. In chemical reactions, usually the substances that you use can either be a chemical element or compounds. So you would see during our discussion today that you would see in these chemical reactions that sometimes we use elements and sometimes we use compounds. So in chemical reactions, there are 6 types of chemical reactions. First one is synthesis, second is decomposition, third is single replacement, or sometimes we call single displacement. We also have what we call a double replacement, neutralization, and combustion reaction. So today we are going to discuss each of these reactions and give some examples on how these reactions occur. Let's start with synthesis reactions. So what is synthesis reactions? What are synthesis reactions? Basically, it's when 2 or more reactants, remember reactants are your beginning substances, when you have 2 or more of these reactants and then you want to form a single product. So 2 or more reactants to single product, and we usually use the equation A plus B is equals to AB. So you have your reactants A and B, and then you create a single product, which is a combination of both of your reactants. So let's give some simple examples that happens during synthesis reaction. Oh, by the way, synthesis basically means to create. So you're creating a single product. You're creating a new compound or a new substance from the combination of your 2 reactants. One of the easiest examples that you probably know by now is 2 atoms of sodium plus chlorine, and you yield 2 atoms of Na, or 2 molecules of NaCl. NaCl usually, you may know this as your common table salt. It's the one that you use to season your food. It's actually a combination of a metal sodium and a gas chlorine. One interesting thing about chemical reaction is that it changes the property of your beginning substances. So for example, sodium is a very reactive element. If you throw a sodium into a water, you can actually create explosion because it's very reactive, while chlorine gas on its own is actually very toxic. Inhaling chlorine can be very dangerous to yourself. But if you combine these two, a reactive sodium and a very toxic chlorine, it creates something that is actually used in our everyday lives, such as seasoning your food, etc. So chemical reactions actually changes a lot of the properties of your beginning reactants or your beginning substances. So this is an example of a synthesis reaction because we combine sodium and chlorine together to create a single product called sodium chloride. Another example that we have is when we have 2 atoms of hydrogen and 1 atom of oxygen. So this combination of both actually creates a 2 molecule of H2O, or 2 molecules of water. Another example is when we have sodium oxide plus water, wherein you create a base, or the base sodium hydroxide. So this is an example of a synthesis reaction wherein when you have reactants, 2 or more reactants, in this case we have 2 reactants, they could be elements or they can even be compounds, and then you create one single product, which is from the combination of your 2 reactants, 2 or more reactants. So that is synthesis reaction. which basically means to create. The next one is called the decomposition reaction. Decomposition reaction is basically breaking down a single reactant into two or more products. And interestingly, this is actually the reverse of synthesis reaction, wherein in synthesis reaction, we have two or more products or reactants, and we create a single product. Sorry, two or more reactants to create a single product. But for the composition, we have a single reactant, and we are breaking it down into two or more product. Example of this is the electrolysis of H2O. If you want to break down H2O into its components, hydrogen and oxygen, you have to break the covalent bond that is bonding these two together. You cannot actually just boil it. Some of you may think if you boil H2O because you see gases escaping, you may think that you are breaking hydrogen gas and oxygen gas, but that's actually not true because the bonding between each atom and the oxygen atom is actually very, very strong. It's what we call a polar. It's a type of polar bonding that you will learn later on when you go to chemistry too. And if you want to break this through, one way to do it is to introduce some form of electricity, such as a picture right here. This is a battery, and you would see there when you submerge a battery inside the water, you would see the gases escaping. It's because the electricity in the battery is using the energy from the battery is being used to break down H2O into its component hydrogen and oxygen. So this is an example of a decomposition reaction wherein you have a single reactant and you're breaking that single reactant into its component atoms or compounds. So that is an example of decomposition reaction. Another example is when you have H2CO3, which is a carbonic acid, and since this is an acid, you can actually what's the term? You can actually just break down the component of carbonic acid into CO2 and H2O. Okay, so that is an example of decomposition reaction. Next is we have single replacement reaction, or you also may see this single displacement reaction. Single displacement reaction is basically when more active substance, it can either be a metal or halogen. Halogen is your group 17. Your group 17 in your table of elements, it's the second to the last column in your table of elements. You would see them usually as the bromine, iodine, all of those are halogens. So when one or more, or when a more active substance or metal or halogen actually replace the position of a less active substance. So this is the usual equation that we use for single displacement reaction, wherein you have A plus Bx. Your A here is your more active substance plus your Bx. Bx here is your compound, and then what happens is you basically switch A and B. Usually X here is an anion, B can be a cation, which usually can be a metal. So here's some example of single replacement reaction, wherein you have iron and you added iron to copper sulfate. And what happens is that since iron is more reactive than copper, copper is being replaced with the iron. In the end, you have what we call a you ended up having a copper plus iron sulfate. So this is an example of what happens when you actually do this reaction in a lab. As you can see here, this is a creation of copper, because what's happened is this beginning iron right here. So you have your iron nail, and then you submerge it into a copper sulfate solution. What happens is that the iron is being replaced with copper, and then the copper sulfate inadvertently becomes iron sulfate. So you ended up having a new pure element or pure substance and a new aqueous solution. Okay, so I hope that is clear. That's basically what's happened. And in your module, you probably will not see this example equation, but there are various examples written on your module. And when you see the letters NR, it basically means no reaction. That is because the substance or the reactant substance that you place may not be a more active substance. So if you see something, for example, that the product says NR, it means there's no reaction. It's because the element or the B element that is present in your solution, for example in this, is more active than the ones that you're trying to replace it with. So for example, if I replace this, so I have a copper sulfate. This instead become my reactant. Let's think of it that way. So I have a copper plus iron sulfate. It will actually not change because iron is more reactive than copper. Reactivity is related to electronegativity. We're not going to deal with that yet, but that's just a little bit of clue on how to identify which chemical or which element is more reactive. It's basically electronegativity. Okay, so but this is an example of single replacement reaction. Next, we have what we call a double replacement reaction. In this situation, we are switching your cations and anions to create new two reactants or to create new two ionic compounds. So for example, this is your first ionic compound AX and your second ionic compound BY, and what happens is that you basically switch the cations from their corresponding anions. So A becomes connected with Y and X becomes connected with B. So you're creating new ionic compounds. So some of the examples, you have your copper sulfate plus a sodium carbonate. So what happens is your copper and your carbonate, this is your cation and this is your anion. You ended up having copper carbonate, and then you have your sulfate and your sodium. You ended up having sodium sulfate. And you may see right here, this arrow right here is just denotes that there is a precipitate formation. When we talk about precipitate formation, it means there's a presence of solid in your aqueous solution. What that means is if you have a aqueous solution basically means a liquid with dissolved substance onto it. So for example, if you take water and then you dissolve salt, there is salt precipitate in your water. So it means there is presence of solids in your liquid solution. So copper carbonate here is in the solid form, but it's basically dissolved in the liquid sodium sulfate. So that's what basically this downward arrow means. So another example is when you take an NH4Cl, which is an ammonium chloride, plus your sodium chloride, you can create a double replacement reaction, albeit you may see it may not be immediately apparent, but what happens is you create three products. But this is still a double replacement reaction because you take your sodium and you take your NH4 here. That NH4, you just take one hydrogen from NH4 and bonded it with OH, creating water, and then creating salt from Na and Cl. So this is basically the double replacement reaction, and there is another product which is ammonia, NH3. So this is a simple video about the double replacement of ammonium chloride and NaOH. So this powder form right here is your NaOH, or your sodium hydroxide, or no, your NH4Cl, your ammonium chloride solid, and then you added your sodium hydroxide base, and what happens is that it creates a double replacement reaction here. We are heating it up. As you can see, there is fire there to actually release the NH3. to test, this is basically to test the presence of NH3. So by adding a litmus paper there, as you can see, this is a red litmus paper in the beginning, but since NH3 is base, it turns that red litmus paper into blue, meaning there is a presence of NH3 there, which is base. And then you have your water and your salt in your aqueous solution, or the liquid that you see that just boiled. So it is a combination of your water and your NaCl salt. So that is another example of double replacement reaction. Next, let's go to neutralization reaction. Neutralization reaction is basically a reaction between acid and base. So if you combine your acid and your base, you actually neutralize both. And what happens is you will always have a product of water and some type of salt. So when we say salt here, it's not always NaCl. It depends on the combination of acid and base that you will use. But you will always have water and whatever some type of salt as your product. So this is the chemical equation that we usually use for neutralization reaction. HX is always your acid because acid always have H, and bases most of the time has an OH or hydroxide. So for example, and then what happens is you create your BX, which is your salt, and then you have your H2O. H2O comes from the hydroxide and the H. So some example is a combination of hydrochloric acid, HCl, and sodium hydroxide. By combining these two together, you actually create a combination of, or you basically create a brine, which is a combination of your liquid H2O or your liquid water and the dissolved NaCl in the water. So here's an example of what happens. So you have your HCl here and NaOH. Equimolar means they're just an equal molar. So we will use indicator to denote the presence, or to tell us whether the substance is acid or base. So since the universal indicator turns pink, it means this is acidic, and the universal indicator turns purple, which means this is a base. So this is our HCl and this is our NaOH. So you have your hydrochloric acid and you have your sodium hydroxide. And if we mix them, you would see that it turns green. Why is that? Because the universal indicator having turns green means it is at a pH of 7. And the pH of 7 is basically, it is neutral. It is H2O. Water is neutral. And you would see there, you would not see there, but there is a NaCl present in that liquid. What that means is that the NaCl is dissolved in your water. So if I boil the water out of NaCl, you would actually see your NaCl precipitate. So that is a neutralization reaction, a reaction between acid and base. The next example is a very simple one called the combustion reaction. Combustion reaction is basically when you react oxygen with your substance, and it is usually accompanied by a generation of light and heat in the form of flame. So what that simply means is if you burn something, you're actually creating a combustion reaction, because burning something is basically combining oxygen in that substance. That substance can be what we call your fuel. So in this case, for example, C6H12O6 is glucose. So if you combust glucose, another word for combustion reaction, you may see this sometimes as your oxidation reaction. There's a little bit of difference between the two, but oxidation reaction is a type of combustion reaction. So when we oxidizes your C6H12O6, you are creating carbons and water. So this is actually very true in a lot of things. For example, you see your matches. Your matches is basically a bunch of carbons. It's all of us, or everything that you see, is actually a bunch of carbons. That's one thing that is true about the earth. We are Most of the matter that you see is actually made up of carbon. And if you burn something, you're actually combusting, you're actually mixing whatever your substance is with oxygen, releasing what we call heat and light. So when you combust something, you usually will see light, and you will feel the heat in the form of a flame. So as you can see here, there is flame here. So this is not glucose. C6H12O6 is glucose, but it's basically the same concept. If you burn anything, paper, fuel, those are a bunch of hydrocarbons. That's basically what most things are. You are actually just also a bunch of hydrocarbons. So if you burn something, you are mixing oxygen onto that material. That's why when there is no presence of oxygen, you cannot actually start flame, or you cannot actually start a fire without oxygen, because you need oxygen to continue combustion, to continue the combustion process. So that's basically what combustion is, reacting oxygen onto your substance. So those are all the types of chemical reactions. We Just a recap: we have synthesis reaction, we have decomposition, we have single displacement, double displacement, neutralization reaction, and combustion reaction. Now let's talk about what chemical equation, and let's try some examples on balancing equations. Well, chemical equations are basically a shorthand of chemical reactions. So we have a lot of chemical reactions that we discuss. The 6 ones that we discuss are the most common ones that is present in chemistry. And in order for us to basically visualize in elements how these chemical reactions are happening, we actually use chemical equation. That's the things that we write. These things right here are the chemical equations, and it helps us visualize how our reactants turned into our products. It's very helpful in chemistry. And we use a lot of symbols. So every time you see gas or this G, L, S, and AQ beside any of the elements, that basically means that the element is in gas form or the compound is in gas form. They're in liquid form and solid form. Aqueous is basically that the substance is dissolved in water, or it's basically dissolved in some type of liquid. If you see an upward arrow, it means there's a formation of gas that is being released. You did not see this in the double replacement reaction because the NH3 gas was not released. It's actually stuck in the combination of water and your NaCl. It was only released after heating up the liquid that you see in the video. But if you see this, it actually means as the chemical process is happening, the gas is released. Okay, you see, so it's not stuck in the product, but it is released in the air immediately. As for the downward arrow, this is basically a formation of precipitate. As for the example in the neutralization reaction, the NaCl from the combination of HCl and NaOH, you do not see the NaCl. It's because it's basically dissolved in the water, and yeah, it's basically dissolved in the water, but it's in there, it's present there. It's what we call precipitate. You would actually see this most of the time if you create a reaction and that the liquid usually has one easy indication is that there is a color in the water. There's a color in the water that basically tells you there's something in there. And perhaps if you boil the liquid out and just have the dissolved precipitate or dissolved solid, precipitate is a type of solid, you would see the powder form that was dissolved in the liquid. Okay. So another thing is, if you see this triangle above the arrow, that just means you apply heat. It could be you burn it using a Bunsen burner, or you added some form of heat onto the reactants in order for you to create your products. So there's a lot of reasons why you want to do that. It could be you want to speed up your reaction. One way to speed up the reaction is by increasing the temperature, and by application of heat you could actually speed up your reaction. Another is if you see substance, usually it doesn't write substance, it's usually the chemical equation of the substance you use. So for example, it could be H2O or it could be NaOH. What that basically means is you use a solvent or catalyst during the reaction. So solvent and catalyst in this situation are not being used, but you use them again. One way or one reason for you to do that is to speed up the reaction, especially a catalyst. What a catalyst does is speed up the reaction in because some of the reactions does not happen immediately. Sometimes you have to wait hours, even days before the product is formed. And one way for you to speed up that reaction is by the use of catalyst, and you would actually discuss this more in general chemistry too. Okay, so these are the common symbols that you would see in chemical equation. Now let's talk about balancing chemical equations. In balancing chemical equations, one thing that you need to understand is the law of conservation of mass. When we talk about law of conservation of mass, it means however amount I start with, I should have the same amount as my product. So the amount of my reactant should be equal to the amount of my product. So what that means is that the mass of a substance does not just suddenly disappear. It should go somewhere. Okay, so the same is true for a lot of the chemicals that we use, more specifically the number of atoms the chemical or an element has. So some tips in order for you to do balancing equation is, first we have to write your unbalanced equation, and then you want to tabulate. I mean, tabulate is you create a table of the number of atoms for each kind of element that is present in your reactant side and your product side. And then you want to adjust the coefficients. The coefficients is basically the number beside or prior to your element. I'll show you later what I mean by coefficient. And you want to adjust the coefficient to balance the number of each atom. So let's try some sample problems. So let's try to balance this chemical equation. So we have CO2 plus H2O, and then we ended up with our C6H12O6 and hydrogen as our product. So how are we going to write this? Let me just change this into my pen. Okay, so we've written our chemical equation. This is an unbalanced chemical equation. So the next step that we had earlier is we want to tabulate, right? So let's write our elements here. So from our chemical equation, we know that we have carbon, oxygen, and hydrogen, right? So we have carbon, we have oxygen, and we have hydrogen. And what we want to do is we want to count the number of atoms in our reactant and the number of atoms in our product side. So this is our reactant side and this is our product side. So what happens now is let's count the number of carbons in our reactant. And as you can see, we only have one carbon. And then we have how many hydrogen? We have two, or oxygen. We have two oxygen here. And then we have one oxygen here. We have a total of 3. But instead of writing 3, what I want to do is I'm going to separate them. This makes it easier for me to count. You can mix them if you want, if it's easier for you. But what I'm going to do is I'm going to write them separately. I'm going to write 2 and then I'm going to write 1 here. So that means I have 3 oxygen. And then 3 oxygen. And then I have my 2 hydrogen on this side, so I will write 2 hydrogens here. Now let's write how many carbons we have on our product. So we have 6 carbons. Now let's check how many oxygen we have. We have 6 oxygen and 2 oxygen. So I have 6 and 2, which gives me a total of 8 oxygen in my product. And then I have 12 I have 12 hydrogen. So how am I going to balance this? Remember, law of conservation of mass, it means the number of reactants I have should be equal to the number of products I have. Since I have 6 carbons here, it means I need to have also 6 carbons here. So what this means is I need to multiply this by 6, right? So what that tells me is I need to write 6 at the beginning of my element where my carbon is. So what that means is I will write 6 CO2. This is your coefficient now. So you write 6, which this tells you that you have 6 carbons. What does this do is also it's not only applied onto the carbon, it also tells you that you have about 6 O2. So what that means is I have also a total of 12 oxygens here, right? So it means I have 6 carbons and 6 O2. What that means, O2 is I have 2 oxygen multiplied by 6. I will have 12 oxygen and I would have 6 oxygen. So that's basically gonna tell you. So that's what happens. So in the end now, I have a total of what? 6 times 2, that's 12, plus 1, that's 11. But before we go on to fixing our oxygen, let's fix first those that we can just change or that is only present in one element, or look for the atom that is only present in one basically one compound in each of the product and the reactant side. So I'm not gonna fix my oxygen yet. I'm gonna focus first on my hydrogen. Okay, so what happens now is in my hydrogen, I have 2 hydrogens in my product or my reactant. I have 12 oxygen or hydrogen in my reactant. So that means is I'm missing basically 10 hydrogens here. So in order for me to make this balance, I'm going to multiply this by 6 as well. So that this tells me is I will have now 12 hydrogens. I have 6. So this now checks out and this will check out, which means I have to add 6 here as well. So that's plus 6 H2O. And again, because I added 6 here, it does not only apply to hydrogen, it also applies to the oxygen here. So I have to multiply this by 6. So this tells me is what? I have 6, 2 times 6, that's 12, 1 times 6, that's 6. I have 18 oxygen. So what I'm gonna do now, in order for me to have the same number of oxygen, I'm not gonna fix my oxygen here. I'm gonna fix my oxygen in my product. Well, I cannot change the coefficient here because my carbon and my hydrogen are already balanced. So the only way that I can fix my oxygen is here because it only affects the oxygen. So what am I going to do? Well, as you can see here, you have your 6 here, you have 6 there, so that basically helps you. So what you're left is you need 10 more oxygen because you only have 2 oxygen here. So what I'm going to do now is by adding 6 here, so by adding 6, C6H12O6 plus 6O2, this tells me that this is 12. So 6 plus 12, I now have 18 oxygen. So that balances my equation. So this would be my answer. So this is one way for you to answer this, or another way for you to answer this is just not using the tabulation anymore and just look at your chemical equation and use analogy and logic. Just keep trying to add numbers or coefficients beside your elements in your compounds until in such a way that they balance. That's actually much easier for me rather than tabulating it this way. I get confused if I do this, but this may be helpful to you or not, but this is one way, or this is another technique that you may use. So let's try another example. So we have silicon chloride plus water creating H4Ci or H4 silicon O4 plus HCl. So what I mean earlier by logic or just by creating, one way to answer this, what I'm gonna do is I'm gonna look at my chemical equation. So I have CiCl4 plus H2O, and then I ended up having H4SiO4 plus HCl. So if I'm looking here, I'm gonna begin with Si. So for Si, I have one silicone at my reactant, and I have one silicone at my product. So that helps me. That it means I don't need to change this here. And then what I'm gonna do is I'm gonna check next my chlorine. So I have 4 chlorine here, and I only have 1 chlorine on my product. So that tells me I should at least put 4 here. So that tells me I have 4 chlorine now here. So I have my chlorine balance and I have my silicon balance. Next, what I have left is let's look at hydrogen. So in hydrogen here, I have basically 8 hydrogen here. So 4 hydrogen there, another 4 there. So that's 8 hydrogen. And I only have 2 hydrogen here. 2 hydrogen here. So what that means is I need about 6 more hydrogen here. So by multiplying that by 4, so that will give me 8 hydrogen in total. And next, I just need to check my oxygen now. So I have 4 oxygen and I have 4 oxygen on that side. So that checks out. So in the end, the answer should be SiCl4 plus 4 atoms or 4 molecules of H2O will yield into H4SiO4 plus 4 molecules of HCl. So that's how you can answer this. Or you can also use the tabulation method wherein you have your elements, you have your reactants, and your products. So if I'm going to write this, I would have SiCl, hydrogen, and oxygen. So in my reactants, I have 1, 4, 2, 1. My reactant. As for my product, I have 1 silicon, I have 1 chlorine, I have 4 hydrogen plus 1 hydrogen here, and then I have 4 oxygen. Okay, so if I look at my Si, so that's balanced. Next, my Cl is not balanced, so I need 4 or 3 more chlorine and my product, so that will be times 4. So that gives me that I should write 4 there. And then what that means, since I write 4 there, this will, my H will also get affected, so this becomes times 4. So in the end, I have what? 8 hydrogen. Alright, so I have 8 hydrogen, and I only have 2 hydrogens here. So I have 8 hydrogen, I only have 2 hydrogens here. So it means I need to at least multiply this by 4. So adding 4 there will give me 8 hydrogen. And since I added 4 there, my oxygen is also multiplied by 4. And that checks out with my oxygen. So let's check. Did we get the same answer? That's basically the same answer. So those are some of the methods that you can use. You can tabulate it, or you can just look at your equation and just use logic and some just logic and math in order for you to answer the balancing problem. So that's all about chemical reactions and balancing equations. If you guys have any question, feel free to message me anytime. And thank you so much. May you guys have a great day.